1998 Ford Taurus with a 3.0 liter engine. We have a trouble code P1131, which is my bank 1 sensor 1, indicates lean. History of this vehicle: it came from an auction and was purchased by one of my former students who brought it here for us to look at. First thing we want to do with a trouble code like this is look at our data stream next. We'll pull up both of our upstream O2s and our short-term and long-term fuel trim, and we'll run the vehicle and take a look at these readings. Okay, scan tool I'm using is the Solus Pro. The screen's a little smaller. I set this to a PID list and did a custom data display to show all of this. So I'm showing all 4 oxygen sensors, my 2 upstreams up top, my 2 downstreams, and then my short-term and long-term fuel trim. This engine is cold, so what I'm going to do is start it, warm it up, probably hold it at 2,000 RPM for a couple minutes, and then we'll come back to the data once these sensors are warmed up. Okay, I didn't let it warm up yet. I wanted to get a shot of this just to show you the activity here. And what you can actually see right away is that my bank 2 sensor 102 is already warm and producing a signal. Now, we're not in closed loop yet. Well, we could be. We got a short-term fuel trim that's starting to move. I don't have my loop status up here. Yeah, we're in closed loop already. That's pretty interesting. I mean, we're talking room temperature here. We're maybe 70 degrees. We just started this car. In a matter of 30 seconds, we're already in closed loop. So you see my bank 2 sensor 102 switching. That's a good one. And the one we have a trouble code for is the bank 1 sensor 1. It's interesting that the computer is not trying to correct that bank 1 sensor 1 and drive it rich. Can you see that on the data? That it's a little contradictory that bank 1 sensor 1 showing us that fixed lean condition. We should see our short-term fuel trim on bank 1 going very positive. So there's maybe a little discrepancy there. But to warn you, when you have a trouble code like this, the computer may already be ignoring this sensor and not trying to drive it rich. And what I would have to do to prove that is probably to clear that trouble code and see if the computer starts to use it again. And I think I'm going to do that next. So I'll see if I can do it with it running here. I'm not sure if it will let me clear the codes with the engine running. Actually, let me not do that yet. Let me change direction here. I want to show you the loop status on the scan tool. Let's see if I can find it. And we should have an indication here of what I'm talking about. It does say closed loop. Now, it doesn't give us a designation on bank 1 and bank 2 closed loop individual. It looks like just one. The loop status does say closed. That's interesting that bank 1 sensor 1's not being corrected for. You see the short term looks normal. So does the long term for that matter. Injection pulse is about the same on both banks. My assumption here is that the computer's using bank 2 sensor 1 for all of its fuel trim corrections right now. Those are heater circuit faults, this data here. That's not going to help me. That's neat. So no other loop status. I was hoping for individual loop status. Bank 1 loop, bank 2 loop, but they're only giving me one. It says it's closed. Again, bank 1 sensor 1 is fixed lean, and the computer is not trying to correct for it based on the fuel trim numbers. So I'm going to try to clear the codes now. Not sure it'll let me do it with it running. All right, turn the key engine off. Turn the key back on.
John.
I'm gonna clear these codes. And again, the reason we're doing this is I'm hoping to show you the computer's fuel correction after clearing these codes. I'm going to do this quickly. If you guys want to know how to configure a data list on the Solus Pro, you have to be on text mode first. Come over here, hit select custom data list, scroll down, deselect them all, and then pick the ones you want to look at. We're going to pick our 4 oxygen sensor signals, and we're going to pick our short-term bank 1 and long-term bank 1 and short-term bank 2, long-term bank 2. And then you hit no, and now we have our list. If you scroll, there's nothing else there except those. Scroll to the left, hit the view, then PID list, and now I have all 8 on the screen. You can actually have the PIDs look bigger too, which would be nice for the camera that we can see that better, but I really want to look at all 8. And we could use a graph. The downside of the graph mode here is it's real small and we can only see 4 of them, and I really want to look at all 8 at the same time. So we're really not worried about graphing the O2 for this video. We can just look at the fluctuation of the signal and say that it's okay. All right, now that we have our codes cleared, we're going to start the car and take a look at our fuel trim numbers. Ignore this short term at positive 24 right now. It's meaningless. The car's not running. We're not trying to correct the ratio right now. Start the car and we'll look at our loop status based on the activity of this bank 2 sensor 102 moving and then the short term moving. We'll see what the computer does with this oxygen sensor now. As soon as I see this short term start to move positive and negative and this bank 2 sensor 1 start moving up and down, then we'll say we're in closed loop. And actually we are right now. It's moving, but it's interesting that the fuel trims are still not trying to correct this bank 1 sensor 1. I'm going to try holding the RPM up, see if that makes a difference. It doesn't make sense. It should be. Let's make sure we didn't set a code again already. Nope, no code. Like this thing's got a memory of where it was. No pending codes. It should be correcting for it. It's not. There's something in this computer's memory that it remembers that this bank 1 sensor 102 is messed up. And it's not using it. All right, shut the key off. I'm going to try one other thing. I'm going to try to reset this computer's keep alive memory. This is a unique feature of Ford's to provide this. And it's this right here, this reset keep alive memory. So there might be something in this keep alive memory that the computer recognized this bank 1 sensor 102 is dead. And it's not using it still, even though I cleared the code. So I'm going to try resetting the cam and see if that brings this O2 back up. Okay, so I reset the cam, go back to our data display, and pull these data PIDs back up again. I really didn't anticipate this for this video. My main purpose for this video is to address an O2 sensor that's lean and to give you guys methods to be confident that it's an O2 problem and not an actual lean condition. So really that was main focus of this video, and this kind of threw me a curveball here. But this might be for good. Okay, start that back up for me again. Now this is after resetting the keep alive memory. I really want to see the computer try to add fuel to bank 1. There it is. Short-term fuel trend positive 33%. See it right there? We didn't see that a minute ago. So that's cool. Even though we cleared the codes on this board, it did not want to use that O2 sensor again until that keep alive memory was reset. So you can see the computer's adding fuel here, 33% on the short term, trying to correct for the lean condition of the upstream bank 1 sensor. You see bank 2 is moving rich and lean. It looks like it just stopped trying to do that, didn't it? Now we're back to both banks moving in unison with bank 2. That's what's going on with this. This computer's pretty smart. So the question with this vehicle, and really with any O2 that's fixed lean, is this an O2 problem, or do we have a lean condition that we need to address on one bank? And there's a quick way to address that. And the next step we're going to do, we're going to add propane to the intake and drive these upstream O2s rich. All right, to show you where we're adding the propane, you see the propane bottle in the picture. We got the air cleaner lid up, and we're just gonna go right into the air cleaner housing. We wanna make sure that we're doing this as a vapor because we have a mass airflow sensor that's after that. We don't wanna put any kind of liquid fuel source in there. With a hot wire mass airflow, you could damage it. So we're going propane in the intake. I'm gonna focus you back on the scan tool so you can see the numbers. Okay, again, purpose here. You see my bank 1 sensor 1 is fixed lean. We're at 0 volts all the time on that sensor. It should be moving up and down just like the bank 2 sensor 1 is. And our concern is that we could have a lean condition on one bank, which most likely it's not based on the way the engine's running. It sounds pretty good. So we either have a lean condition or we have an issue with the O2, and this propane test is going to address that. When we add the propane, if you keep your eyes focused on the bank 2 sensor 1, in fact I'll make that a little bit easier for you guys to see. Change this to a 2-PID list, and what we'll do now is we will focus. There's my bank 1 sensor 1 that's dead, and there's my bank 2. When we add propane, bank 2 is going to go full rich, and so should bank 1. So go ahead and do it. Full rich on bank 2, that was an immediate change. We're over 800 millivolts, that's what we want to see. Notice bank 1 is not responding at all. Okay, shut the propane off. This is not a lean condition. We absolutely have an O2 sensor problem. Okay, so let's think about our possibilities here. We know we don't have a mixture problem now. We know we have an O2 problem. It could be the sensor itself. We could have a wiring problem, or we could have a computer problem. And the wiring, my main concern would be, is my signal wire shorted to ground? Is there a possibility of a wire that's pinched somewhere in this harness pulling the signal down all the time? The chances of this being a bad ground wire are slim to none. Bad ground wires on sensors generally drive the voltage high, so I'm really not worried about a bad ground here. I'm concerned about, say, an open in the signal circuit. Remember, we're using scan data. We could have an open where the signal's good at the sensor but faulty at the computer. Or we could have a short to ground in that signal wire, And the next test that I want to show you guys addresses those very, very quickly. Okay, it's important to do your homework and figure out which bank is which. We've already done that. Our firewall side is bank 1, so bank 1 is on that side, and bank 2 is up here next to the radiator. And what I want to do first is I'm going to focus on bank 2 because bank 2 is a known good circuit. We know bank 2 operates. And one of the things that I like to do when addressing wiring issues for oxygen sensors is to unplug the sensor and look for a bias voltage. A lot of our computers use bias voltage that runs to the O2. We can use that bias for testing purposes. This will be sections 4 and 5 in my book. We talk about bias voltage testing. Fords, as I have listed in my book, do not use bias voltage, but this would be one method you could determine that. If you didn't know that, how can we tell if this vehicle has a bias line or not? It's simply unplug one of the oxygen sensors and look at your scan tool. So I'm going to unplug my bank 2, this one right here that you see in the picture. I'm going to unplug that connector, that green and white connector for the O2, and I'm going to focus you on the scan tool. If this has a bias line, what we'll see when we unplug that is around 0.5 volt on the scan tool with that sensor unplugged. So I'm reaching down, I'm going to unplug this so you can see here. O2 is unplugged. I'm going to get you focused back on the scan tool. Okay, my O2 S21 on the screen here, which is my bank 2 sensor 1. That's the one I just unplugged. Why am I using that sensor for this test? Because it is a known good working circuit. That's important. You can see on the scan tool, with that sensor unplugged, we have 0 volts on that signal wire. So there is no bias line on Fords that we can use for diagnostic purposes. If this had a bias voltage, it's as simple as unplug the sensor. If your voltage goes to 450 millivolts or 500 millivolts, your circuit is good and your oxygen sensor is bad. It's that quick of a test. Remember where we are. We're at 0 volts all the time. If we unplug the sensor and that bias goes to 450, the signal wire is fine, put a sensor in it. I have a video or two, I'm showing this already. It's already up on YouTube. So look for that. On this one, we can't use that test. So I'm going to show you another way that we can quickly verify signal circuit integrity on this car without disconnecting the computer and disconnecting the sensor and ohming the wire for opens and shorts like a manufacturer flow chart is going to want you to do. Okay, what I'm going to do is I'm going to show you this test on bank 2, which is up front. And the reason I'm going to show it to you here is I can actually get the camera on this sensor connector where I cannot on bank 1. So I'm going to show it to you up here, show you the test on bank 2, and then we'll do it on bank 1 to be sure. But I want you guys to see what I'm doing. So I'm at the 4-wire O2 connector, and this is where it helps to know your sensor side colors. This is why I have this listed in my book. 2 whites, a black and a gray, universal Bosch colors. And you can see in the picture to the right that we have that on this connector. So this side of the connector we have our 2 whites, we have a black and a gray. And so I know my black is the signal wire. And so what I'm doing is I'm looking at where the black pin goes in on the sensor side, and I'm T-pinning that same wire on the harness side. So sensor side, harness side, you see my T-pin in the picture. I'm going to unplug the sensor now, get it out of the picture. So now what you should see, hopefully still in the camera, we do is my T-pin on my signal wire of my bank 2 upstream O2. And what I'm going to do is I'm going to touch battery positive with one finger, and I'm going to touch my T-pin with my other finger. I'm going to drive a small voltage through my body into the O2 signal wire, and I'm going to look for the scan tool to change when I do it. So I'm going to get you focused on the scan tool. Well, let me give you a shot of where my hands are going to be. So let me zoom out and I'll show you my fingers here. One's going to be on battery positive and the other is going to be on that T-pin. And I like to lick my fingers when I do it because it gives you a little better connection. So lick my fingers, touch battery positive with this hand, touching the T-pin with this hand, And I'm going to get you focused on the scan tool now, and we'll talk about the result of that test. Okay, so what I'm doing is I'm driving a voltage through my body into the signal circuit, and if the signal circuit integrity is good, so no opens and no shorts in the signal wire, I should see a voltage increase on the scan tool. Now we might not see exactly the voltage I'm putting into the circuit. Remember, oxygen sensors only produce 0 to 1 volt. So the computer's program is not designed to read anything more than a volt. So we probably aren't going to see exactly the number that I'm putting in here. And I'll get you a shot of that on a voltmeter so you get an idea. Our main concern when we do this test, we want to see the O2 millivolts go over 1000 millivolts. I want to see 1 volt on the O2 signal circuit on the scan tool. So watch, here's the test. Again, battery positive with one hand, touching the T-pin with the other. And you see a millivolt change on the scan tool. We're reading 1600 millivolts or so. That is a good test. There's nothing wrong with the signal circuit on this O2. Now we know that bank 2 is the working sensor. This is the test we need to do on bank 1 to ensure that our circuit integrity is good. And if it is, then we're going to be confident to put an O2 sensor in this. Now you might be thinking, well, don't you want to check the heater circuit? And the answer is no. I don't need to on this vehicle, because a inoperative heater circuit, we would still have O2 activity. It would just be very sluggish and slow. It would be a good idea still to maybe check your heater, power and ground, just on principle, but the main thing for this video, what I want to show, is signal circuit integrity. Opens and short circuit testing on the signal of an O2 can be done very quickly if you think about what you're doing. So I'm going to move my T-pin to the back. I'm going to keep you focused on the screen. I'm going to do the test on the bank 1 sensor 1, and we'll see the result of that. And we'll talk a little bit more about it. Okay, when we did the front one, or bank 2, I unplugged the O2 sensor connector. The reason I like to unplug the O2 sensor connector is if the sensor's shorted internally bad enough, when you do this test, it'll pull all the voltage down across your body and you won't get the reaction you want. So the reason I unplug the sensor is to get that variable out of the mix. For the back one, I'm going to leave it plugged in and we're going to try it plugged in. If it doesn't work plugged in, then we'll unplug it and do it. Just wanted to address why I unplugged the sensor. So I'm going to do the test. Touching battery positive with one finger, touching my T-pin with the other. And you see on the scan tool we had the same number, 1600 millivolts plus. So what that tells us is our signal circuit integrity from the sensor all the way to the computer is good, and that we're not worried about an open or short to ground in the signal wire. That's what that tells us. Sensor itself is dead. We feel confident changing it. I want to address one more thing, and that's the voltage level that I'm putting into this circuit. I'll get you a reading on the voltmeter. Okay, what I'm going to show you first is what a voltmeter reads just by me touching the positive lead. So I'm just going to hold my finger here on the positive lead, touch my other hand to battery positive, and you see I'm reading battery voltage. I'm reading 12.2 volts. So that's through my body. If I lean my hand on something metal, see if I can drop the voltage in this circuit. Need something touching the, there you go, I'm touching the alternator housing now. And you see I had like 6 volts there, 7 volts. So there's basically a small amount of current flow through my body that's causing that voltage drop. Remember, my body's the resistor. So on the O2 circuit, I'll get hooked up to that. This is the signal wire. I'm just using a jumper wire on the end of my voltmeter positive lead. I have that jumper wire on the signal. And you can see the T-pin in the picture. So what I'm going to do is I'm going to reach down, touch that T-pin. You can watch the voltmeter and see what kind of voltage we're actually putting into this oxygen sensor circuit. So touching battery positive, touch the T-pin, And we got 12 volts there. I'm not making contact here. I need to put my T-pin in better here. Hang on. I knew that based on the voltage level, and the scan tool did not change for that one. Okay, let's try it again. Battery positive. Scan tool is reading 1600 millivolts, and I'm reading 6.5 volts on the voltmeter. So am I putting more voltage into this circuit than is designed through my body? Of course. I just put 6.5 volts into the O2 sensor signal circuit. There might be a concern for some of you guys for that number. I guess the short answer for this is I've been doing this for 20 years and never hurt one. So that would be, experience would be key. I know I'm putting more voltage in the circuit than what's designed. In fact, there are some that claim when you do this test that you're only putting 1 volt into the oxygen sensor circuit because your body has high enough resistance. That's completely untrue. I just proved that we're putting more voltage than 1 volt through our body into this circuit. There's no current flow, I think, is the key. Current flow is heat, and heat is where you get damage. Am I putting higher voltage in this circuit than is designed? Yes. I'm not the engineer. I don't make the voltage sensing circuits in the computer. I know that what's given me confidence here is over the years where you have these cars come in the shop and the heater circuit wire shorted to the signal wire. So a direct 12 volt feed that you would think would damage the computer. In every single one of those repairs, once I took that heater away from the signal circuit, everything was fine. So I've seen direct 12 volts shorted into a signal of an O2 and not hurt the computer. And I've seen it on multiple occasions. I'm comfortable with what I'm doing. The reason I do this test is this allows me to not have to dig the computer out of the dash and find the O2 signal pin and do opens and short circuit tests. So what's going to take you 45 minutes to do takes me 2 minutes to do the same thing. So O2 sensor PCM response test is what I call it in my book. We take and we add a little voltage to the circuit. We look for the computer's response. You saw on the voltmeter that we read about 6.5 volts, so there is a certain amount of current flow, you could call it, inside the computer sensing circuit that's dropping the voltage on my body. It's not going to be a current flow that I can measure. I guess maybe we could try that. For those of you that want a amperage reading, we could switch this to amperage and I can do the same test and see if we can read it. I guess we'll add that. That'll be the final thing we do here for the naysayers out there, is let's see what kind of current flow that I'm pushing through my body into this O2 signal circuit. So that's real easy. All I'm going to do is switch this to the amp port. My leads are already connected, but in this case, I need to have my body in series to this. I'm going to move my multimeter lead, so one lead's going to battery positive. So my black negative lead on my voltmeter is now connected to battery positive. This red lead I have in my hand. So my hand is really going to be between my jumper wire. Let's make sure that got this in the shot here. Yeah, we're good. My body's going to be in between here. We're on an amperage scale. This is actually on the decimals to the right of the 0 are milliamps. I'm going to hold my fingers on this. Again, this is O2 signal wires right here. This is going to be battery positive right here. And I'm going to lick my fingers and touch these two and see if we get an amperage reading. Absolutely no measurement of current flow there at all. Take my hand off, you see the same number, 0.001. Touch them together. And I guess to prove to you what I'm doing, I'm going to take a test light, connect it to ground to show you that my meter is hooked up properly for this. And if I did this right, this test light's going to light. So you can see that I definitely have battery voltage on the tip of my multimeter lead. You see there's actually the amperage of my test light, 185 milliamps. Do the same thing. Put my hand on this. My body's the resistor. Put my hand on this. This is the signal wire. No amperage whatsoever. Am I going to hurt the computer with 0 amps of current flow? I don't think so. So I'm comfortable with it. It's a sensing circuit. Sensing circuits in the computer are high impedance circuits. We don't need to worry about this. It's a good test. Okay, I'm going to add one more thing to this because I have another video where I'm showing this. And I did it differently. I used a test light instead of my body. And I want to show you the test light result doing the same thing. Remember our first test. So I'm back to voltage. I have this rigged up a little different. I have my voltmeter connected here. This is my signal wire going to the sensor. And if I touch this one, this is my one hand on this lead. I'm basically touching the signal circuit. Lick my finger, touch battery positive. And we got 7.5 volts. We had 6.5 last time. I think I'm squeezing a little tighter on this lead. So using my body, we're driving 7.5 volts into the O2 signal circuit. Scan tool's reading 1.6 volts right now. So the test is good for circuit integrity like we're doing. So that's using my body. In my last video, I used a test light to do it. So now the test light's connected to battery positive. I'll show you this light's going to light when I find a ground here. Should light. Find a good enough ground, it should light. Sure if that camera's zoomed out that far. Find a ground on the... There you go, see? Test light's connected to ground. Sorry. Test light's connected to ground here. Test light is connected to battery positive. So when I find a ground, test light lights. So the tip of my test light has 12 volts on it now. In my last video I showed that I used a test light to do it. So I'm going to do it again. Have my voltmeter connected here so you can see it. Voltmeter's connected to the signal wire. This alligator clip is the signal wire. I guess I'll get the scan tool in the shot here to prove it to you too. So this right here is the signal. Test light to battery positive. Touch on the signal wire. You see we're at 12.2 volts. We're actually sending 12 volts into the O2 signal circuit now. You see the scan tool respond. No problem there. Same test using a test light. So we got higher voltage with the test light. Some of you might like to use your body because it's a lower voltage. I've done it with the test light for years too. I'm going to do an amperage check now. Same thing we did before. I'm going to move this over to my amp port, switch this to DC amps. I got to do a little changing around here with my leads on my battery. So now my negative lead is now connected to battery positive for my multimeter. And that makes my red lead. This is going to be battery. So battery positive coming in here, battery positive coming out. That's the way ammeters are designed. You can see the test light's lighting. Test light's connected to ground now. Test light is lighting, showing you amperage of the test light. So what I'm going to do is I need my test light in series now. So think about this. It's hard to follow. This is battery positive right here. This is my O2 signal wire right here. I'm going to take my test light and put it between, I need it in series. To measure amperage, you have to be in series. So my test light's going to be connected, one lead to here, this is my signal wire, and then the other lead to the test light itself. You see the scan tool change, so we're definitely doing the test. Test light is in series, 1600 millivolts, absolutely 0 amps change with this test. So hopefully that addresses that. No current flow. Higher voltage using the test light, yes. Lower voltage using your body. Why? Because your body has more resistance. Is there current flow taking place in the circuit? There has to be for there to be a voltage drop across my body. But it's so small that I cannot measure it with my multimeter. And it was the same result with the test light. So hopefully that addresses that, and you guys have a little more confidence in this test. One last thing would be the sensor connector and leaving it unplugged or plugging it in. I think I remember at one point in time having to leave it plugged in to do this test because of the sensor ground circuit. So just be aware of that as you're manipulating circuits and doing bypass type testing, is the sensor may actually need to be left plugged in at times. On this Ford, that wasn't the case. We were good unplugged. But if you don't have the result you want to have with a sensor unplugged, try it again with it plugged in. A Ford mass airflow sensor with the 2 grounds is a primary example of that, where you have to leave the circuit plugged in to get a response, because the computer actually grounds at the sensor itself. Okay, I have the new O2 installed. Get you a final shot. Make sure you guys are comfortable with this fix. Can you go ahead and start that for me? We'll watch our bank 1 sensor 1 and our bank 2 sensor 1. This will help you guys make sure you're comfortable with what we did. Look at O2's already reacting. That bank 1 sensor 1, it reacted like right now. So these heated O2s, man, it's the advantage of using the heated O2 is it allows the system to enter closed loops so much faster than they were ever able to before. And I didn't hold the RPM up or anything to warm the sensor up. You can see the heaters are functional, no question about it. If the heater circuit was not functional, that bank 1 sensor 1 signal wouldn't be reacting the way it is right now. There's really no need to graph it, but I can do it. So both O2s moving rich and lean. You can see I did not damage this computer with my test light bypass test or test light integrity test. We didn't send any additional amperage in. Use your body. I think it's safer. I've used the test light too, to each his own. This is a good case study. It's a good review of some keep alive memory and what the computer was doing with that fuel trim, and remembering that that sensor was faulty. Pretty neat on the insight on the strategy of this car, that the computer was smart enough to use bank 2 as its total fuel trim control for the engine instead of over-richening bank 1. That's pretty neat. I had to clear the keep alive memory to make that bank 1 react again. So that was cool. And then a little quick test for integrity in the O2, and then maybe to give you guys some confidence that what we did was completely safe. So that's it. I think what I'm going to do, I'll make a part 2 of this because I have a Ford, and I mentioned integrity testing and why you have to leave a sensor connected sometimes and why you don't, and on some you don't. So I'm going to do a part 2 where I'll do a mass airflow sensor integrity test, and I'll show you on this design we have to leave it plugged in. So look for part 2.